All right, I guess I'll start then.
Yeah, go ahead.
Can everyone hear me?
Yep.
Okay. So this paper kind of considers a problem that hasn't been looked into before, or a potential problem, with incomplete unit cells at the boundary of these nanocrystals, which this becomes more and more important as crystals get smaller and smaller. You have a higher, or the contribution of these incomplete unit cells becomes more and more dominant. And this could potentially have implications on future phasing algorithms that are trying to use more information between Bragg peaks. The paper kind of looks at two cases. First, it does a 1D crystal case analytically, and then it numerically evaluates a 2D case. So first, I'll start out kind of going through the background. This paper is considering unit cells that consist of just two molecules. You can see this would be the crystal and the unit cell in the box. You could break this unit cell into two parts, an asymmetric part, which is A, and then its symmetry pair, which is related by a rotation and then a translation. You can build up the sublattice for this crystal for each the asymmetric and the symmetry pair by just defining the occupancy for each lattice point. For example, this lattice point here has both the asymmetric and the symmetry pair occupied, so the occupancy would be 1 for both of these. But for example, this lattice point only has the asymmetric unit occupied, so the symmetry pair would have 0 occupancy. And if you wanted to define the electron density for the entire crystal, all you need to do is take the convolution of the asymmetric unit and its sublattice, and this essentially inserts the asymmetric unit at each lattice point that should have an asymmetric unit, and likewise for the symmetry pair. The nice thing about this construction is that when you take the Fourier transform, you just get the product of the Fourier transforms of the asymmetric unit and the sublattice. So if you want to take that one step further to the intensity that you'll measure at the detector in terms of Q, which is a measure of the momentum transfer, you can nicely define this function in terms of the sublattice, the asymmetric unit, and the symmetry pair. So first, the paper looks at just a 1D crystal. They use this F because of its. You can divide this unit into two Fs, and there are 4 types of crystals that they consider here. The first 2 have complete unit cells throughout the crystal. Type 2 is just created by translating the first F by half or by 1 unit cell length, and then type 3 and 4 have incomplete unit cells at their boundaries. So if you look at this 1D crystal with the construct that was outlined above, you find that the average scattering intensity of all 4 types of crystals is just equal to the average scattering intensity of 1 and 2, less the missing molecules at the boundary in 3 and 4. Next, the paper looks at a 2D crystal, which is just composed of more of these Fs, where this shows the asymmetric unit and its symmetry pair. And you can construct 4 unit cells from this asymmetric unit. These were the diffraction patterns that they computed for each combination. And then this is just the diffraction pattern from the asymmetric unit by itself and its symmetry pair. So again, they're trying to look at the effect of having these incomplete unit cells on the boundary of the crystal. So what they did is they constructed 500 crystals that have random edge terminations, and they computed the diffraction pattern for each. So this shows what a typical crystal might look like, and then the typical diffraction pattern. And they wanted to compare the results of these 500 diffraction patterns with the diffraction pattern of each of the 4 unit cells. So what they did is they just took the incoherent superposition of each of the 4 unit cells and summed it up. But they need to remove the contribution of the lattice transform from the 500 diffraction patterns. So after computing the average of the diffraction patterns, they divided out the lattice transform. And next they just computed the normalized difference. And they found that with a scaling factor, eta, they minimize R by changing eta. This, I think, just takes into account the different intensity caused by the size of the crystal versus just the 4 unit cells. And the result was that it is actually well approximated. The diffraction intensity is well approximated by just incoherent sum of the 4 unit cells. Next, they wanted to move from, or see if they could move from these 500 diffraction patterns back to just the asymmetric unit. And kind of as a first pass, they assumed that the computed diffraction intensity would just be the incoherent superposition of the 4 unit cells of the computed asymmetric unit. So in order to do this, they use 2 projection operators. The first projection operator, P sub I, puts the computed intensity in the same scale as the measured intensity. And the second projection operator, P sub S, is a support projection, which in my understanding uses the information that you know that the asymmetric unit should be finite size. So each iteration, it's closing down the support in which you can have a defined electron density. And they alternate between these 2 algorithms to get to the next electron density. The first one is difference map, and then the second one is error reduction. And after about 2,000 iterations, they converge to this result. And again, similar to the first step in the 2D crystal simulation, they wanted to compare this to they wanted to compare their computed asymmetric unit with the average of the 500 diffraction patterns. So they took the asymmetric unit and then constructed the 4 unit cells from it, and based on their assumption, they just computed the incoherent superposition of the 4 units and computed the difference between that and the 500 diffraction patterns. And they got the same result as in the first section, 0.07. They suggested this could be limited by the assumption that the diffraction pattern should be the incoherent superposition of these 4 units. One suggestion they have for future work is using more of the information kind of outlined in the 1D crystal case, rather than just making this assumption. So in conclusion, this study is kind of useful for maybe future algorithms that are using more and more of the information away from Bragg peaks. These considerations may have a bigger role. And as I mentioned before, perhaps a more robust algorithm that's using more of the information could be developed. Thanks for your time.